Okay, let's look at some practice problems. Here we have a circuit as an example of a system. This is a schematic of a circuit. And as we mentioned, a system model basically imposes constraints on various variables. In this particular setting, the circuit elements impose constraints on the currents and the voltages in the system. So in general, we would have 2 node voltage equations or 3 mesh current equations or 7 device equations. We could write the equations in either one of these forms, and each of these forms basically corresponds to a constraint on the system. Now the system itself has important variables associated with it. So clearly the voltages, the currents. So notice this Y is U is a current. I'm sorry, Y is a current. U is a voltage. And so these are important variables. Unimportant variables are all the other voltages and currents. So for example, the voltage at this point right here, which is in between these 2 nodes, is not so important. So here, now I write an equation that involves only the important variables. And in this case, I write node voltage equations. Well, actually, I wrote a node voltage equation associated with these 2 nodes, and then a current equation associated with this inductor. And so those are the 3 equations I get. And then these 3 equations are all the equations I need to completely describe this circuit. So notice I have basically an equation associated with each what is called a memory device. A memory device or a storage device. So remember, a capacitor stores charge. Inductor stores magnetic flux. And so we have these equations. So notice that I have a first derivative associated with each of the capacitor voltages, and I have a derivative associated with the inductor current. So this is an example of a model. So these are the equations associated with this schematic. I can have other equations that come from various other relationships. So for example, we have what's called the Volterra predator-prey model, where N1 is you have an island with goats and foxes on it. Okay, N1 is the number of goats at time t, N2 is the number of foxes at time t. On the island, goats eat vegetation, foxes eat goats. Okay, and you can go through and show that the population change on the island can be written in terms of these 2 equations with some constants A, B, C, and D. So this is a predator-prey model. I can talk about image smearing. An object has light intensity reflected off of it, U, in terms of X and Y, so 2 dimensions. So this is on a plane. This image passes through a lens system that is linear and translation invariant. So translation invariant in physical space is very similar to time invariance in time space. The image lands on a focal plane with this intensity. Okay, so you have some blurring function. We have our input image, and the output is actually this convolution. And if h is given by this function, then we have what's called Gaussian blurring that occurs. So this is a 2-dimensional system. The input is 2-dimensional, and the output is 2-dimensional. Okay, the system is this lens system. Okay, linear systems. Let's take a look at the differentiator. So if I differentiate this weighted sum of x and y, I can go through and show that this derivative can be broken up into the sum of two derivatives, and this shows that in fact the differentiator is a linear operator. Okay? This, again, just based on the definition of what a linear operator is. Similarly, if I take the same input function and integrate it with respect to time, I can break this integral up into the sum of two integrals, a weighted sum of two integrals. And so we can see that in fact the system is, the integrator is a linear operator as well. What about norm? A norm needs to satisfy what is called this triangle inequality. And so the question is this linear? Is this linear? Well, I can see that here I have alpha here. Notice here I have alpha, here I have absolute value of alpha. This is not alpha. In fact, it may be negative alpha, depending on whether alpha is positive or negative. So I can see that right away, without too much hullabaloo, I can say that this norm, which satisfies this relationship, is not a linear operator. Now also, because I don't have equality, I have inequality. That's also a giveaway. Okay. Similarly, so the norm is not a linear operator. Okay, what about the integrator? Is the integrator memory or memoryless? Okay, so y is given by the integral from t0 to t of u of tau d tau. U is the input function. Okay, and we can see that the output y at time t depends on the value of the input before time t. In fact, it depends upon all the values of the input from t0 to t. So it is a memory function. It's a memory operator. All right, consider the operator S given by this expression. So it is a convolution on U. All right. And let's consider this input signal. U of t is given by this. So if we go ahead and plug this in here and perform the operation, the integration, this is what we get. We get this function, which is a function of time. If now I truncate that signal, this is what I get. If now I first truncate the input signal and then operate on it by S, then I get this expression, which is kind of nasty, but it shows that the output is much more complicated than just applying the original input to the system. If we simplify this, we get this expression. And we can see that this expression for the output is not the same as the original expression. So, and in particular, if we let T1 equal to T2 equal capital T, we have this expression for PT, the truncation operator operating on S, and we have this expression for the truncation operator operating on S, operating on a truncated version of U. So we have different functions here showing that this system is not time invariant. So since these are not equal, the system is not time invariant. So why is it not time invariant? Well, look what happens, for example, at t equals 0. When we let t equal 0, we get this expression. This expression depends upon u for time greater than time 0. Okay? So this is a constant. I'm sorry. this is independent of time t, but this integral then depends upon the values of u actually between 0 and pi. And so this is not time invariant, and it's not causal because it depends upon future values of, so at time 0 this integral depends on future values of u, so it's not causal. So it's not linear time invariant and it's not causal. I'd like to give you now an example of linearization. The system I'm going to be using for linearization is a magnetic suspension system, for which I have a video here. So this shows that there's a globe with an electromagnet that is supporting the weight of the globe so that it can float. This actually requires active controls in order to make this happen. But this is not just a theoretical example, it's a practical example as well. So here is our magnetic suspension system. It can be described this way. I have a globe with a magnet in it, and I have an electromagnet in the top, so that the north and south attract each other, and the force of attraction is given by this equation. So if we write a force equation for this system, we have the mass of the globe times the vertical acceleration is equal to sum of the forces in the downward direction, mg, that's the gravity force, minus the force upward, which is this force. And so we have an equation that describes the magnetic suspension system. We wish the globe to maintain a position ye at equilibrium. So you saw it floating at state constant at a particular position. At equilibrium, we have this equation must be satisfied, right? The second derivative must be equal to 0, and also the first derivative must be equal to 0. Actually, all derivatives must be equal to 0. So I take this equation and I can solve this equation. So given y is equal to ye, I can solve for ie this way, where we assume that all of this is positive and that this is positive. Okay, so all of this is positive. So anyway, this is the equilibrium current. So we have an equilibrium position and equilibrium current. Because the electromagnet is a coil, it satisfies this equation. It has an inductance. It satisfies this equation, or an equation like this. Actually, this is a simplified version, but so in equilibrium, the current cannot be changing, so this goes to 0, and so we have the equilibrium voltage. Okay, and it's given by this. So notice we have an equilibrium current that we saw earlier that's determined by the equilibrium position, equilibrium voltage. So y, well, this equation also has to satisfy an equilibrium condition. We define the states z1, z2, and z3 as every variable that has a first derivative in the system. So y has y dot as a variable, y dot has y double dot, and we saw that, and I is L di dt, so that has a derivative. The input u, the output y, and we get these three state equations. z1 dot is equal to y dot. So if I differentiate this equation, I get this, but y dot is what we called z2. z2 dot is the same as if we differentiate this equation, y double dot, and going back we can go through and show that that is equal to this quantity, okay, where I can substitute in for I and for Y as Z3 and Z1. And then I have the inductance equation, L di dt, I can solve this way. And so this gives me Z3 and V. So I can write the first derivative of all the state variables in terms of only the state variables and the input. So this is in terms of the state variables and the input, state variables and the input, state variables and the input. So here's our state equation. Z1, Z2, Z3 dot is given by this vector, which is a function of Z and V. Remember, Z has Z1, Z2, and Z3 in it. And so we have functions 1, function 2, and function 3, all functions of Z and V. In this case, our V is a single input, so it's just a scalar. So that's our system. That's our state equation. The equilibrium condition is the condition that makes this, puts the system in equilibrium. It's what makes this equal to 0. We've already solved for the equilibrium condition, and this is what we get. Z1e is equal to YE. Z2, remember Z2 is Y dot. And so this is just saying that the derivative, first derivative of Y must be 0. And then we have this equation that is the force balance equation. And then we had that VE was equal to R times IE. So we have the equilibrium condition on Z and V. So for linearization, we define x to be z minus ze, which is this. Okay, and we want to find the matrices A, B, C, and D to make this linear model. So again, the partial of f, so this is f with respect to E, and I'm sorry, the partial of f with respect to z, so we would take the partial of this with respect to z, partial of f with respect to v, so notice that, this is x, we actually need to do f, and g, in this case, y is just the output, so in this case g is just y, so that's easy. Okay, so when we take the partial derivative of f, so here is f. I'm going to take the partial derivative of this with respect to z. So that's the partial derivative of f with respect to z1, partial of f with respect to z2, partial of f with respect to z3, partial of, and then the partial of f with respect to v. Okay, so that's what we need to do. So the partial, so notice that f itself has f1, f2, and f3. So I take the partial of f1 with respect to z1, partial of f1 with respect to z2, partial of f1 with respect to z3. In this case, f1 is just z2. Partial of z2 with respect to z1 is 0. Partial of z2 with respect to z2 is 1. Partial of z2 with respect to z3 is 0. In this case, it's simple because our function is simple. Next, we take the partial of the second variable, partial of f2. That's the second row in our equation. So again, with respect to z1, z2, and z3, and evaluate at the equilibrium conditions. So this is the function. I'm going to take the partial of that with respect to z1. So notice z1 does appear in here. So when we take the partial of all this with respect to z1, I get this expression. So notice that went from squared to cubed. The g term went away. And now we evaluate at the equilibrium condition. That is, when z3 is equal to z3e, z1 is equal to z1e. When I plug those values in and simplify, it boils down to this quantity. Partial of f2 with respect to z2, here's my function. It's not a function of z2. So when I take the partial of it with respect to z2, I get 0. Partial of f2 with respect to z3, it is a function of z3. And in our case, even though we have absolute value signs, because of our equilibrium the way we've chosen it, z minus I naught is always positive. so we can drop the absolute value signs. So when I take the partial with respect to Z3 and evaluate at the equilibrium condition, I get this expression. So it simplifies down. Okay, so that's the second equation, second row. Third row has this. So I'm taking the partial of F3 with respect to Z1, Z2, and Z3. So here's F3. It is not a function of Z1. It's not a function of Z2, but it is a function of Z3. So this is what we get. Similarly, we compute the partials of F with respect to F1, F2, and F3 with respect to V. So in this case, F1 is just Z2. Partial of that with respect to V is 0. Partial of this with respect to V, since this is not a function of V, it's equal to 0. And then here we have this term. This is a function of V, so partial of that with respect to V is just 1 over L. Our output equation, G, is just Z1, and so I take the partials with respect to Z1, Z2, Z3, and V, and I get this. So, putting it all together then, we have this state model. This then is a linear approximation of the model of this system evaluated at the equilibrium condition. So this is an example of linearization. Thanks for watching this lecture's videos.